Okay, so chapter 3, we went through most of this today. All about vectors. I think we've even done this slide when we started, but what are vectors? Vectors are any quantity where you have magnitude and a direction. Okay, so as long as we put a direction on there, that is a vector. 50 miles per hour north, it's a vector. 3 newtons downwards, that's a vector. So you notice the differences here. These are simply magnitudes, or simply amounts. Distance is 5 miles. I have no idea which way. That makes that a scalar. And again, you often see the little vector hat, the little kind of half arrow above the variable to indicate that it is a vector. So of course we can represent vectors graphically. And one way is, of course, to use the Cartesian coordinate system. Also compass directions, which, let's make sure we are aware. East would be like what degrees in the Cartesian coordinates? What?
0.
It'd be 0. And then north would be what? 90. Okay. So remember, we go around sort of counterclockwise. 0 degrees, 90, 180, 270. Back to 360, or also 0. Either way. Vectors are drawn to scale. So in this case, I had like 8 meters per second due east. Please don't be thrown by the fact that it's a velocity. It doesn't just have to be distances that we can graph. I mean, that could have been anything. A force, acceleration, velocity. If I want to make it negative, that would just simply mean the opposite direction, so that would be west. And as a vector simply is pretty much drawn as an arrow, but the way the arrowhead is pointing means something. That's the way the velocity is going. It's the way your object is moving. So that's called the head of the vector, and then that part we call the tail of the vector. So they can be placed anywhere on a coordinate system. We don't always have to start our vectors at the origin. We usually start 1 there. But they can be placed anywhere, so long as their magnitude and direction are the same. So looking at these 3 pictures, which one represents all the same vectors? See. Remember this from 9th grade? Okay. So A's got the same direction, but obviously different magnitudes. B is supposed to have all the same magnitudes, but obviously different directions. And C is really all the same vector. Doesn't matter where I put it. This is still representing the same thing. Okay, so in the problems you'll see in the book, there's really 3 different ways that they'll tell you the direction of a vector. But you can really place all in the Cartesian coordinate system anyway. So of course, the Cartesian coordinate system would be number 1, the 0, 90, 180, 270. And just simply with compass directions. Come on. Here we go. Almost. So this one should be easy to draw, just not being very accurate about it, but hopefully close. 5 meters at 135 degrees would be going which way? Yeah, up and to the left. It's between 90, it's between 180, it's in fact exactly between them. So there we go. That could be my vector to represent 5 meters at 135 degrees. Over here, what if I said 25 degrees east of north? Yeah, it is kind of northeast. Which way? Yeah. When it says east of north, like start at the second direction. So start at north and move towards the east. So it'd be, like this, where that would be your 25 degrees. So you will see that a lot. If you see something that just purely says northeast, that would mean right smack in between at 45 degrees. Otherwise, it should say something, this of this. All right, and then your other sort of directional system is just relative to a horizontal or vertical. You'll often have, like, okay, somebody's pulling on a rope, and that rope makes an angle of 15 degrees with the horizontal. But you just have to realize that with the horizontal, you can mean two. In all honesty, it could really mean 4 different possibilities. But if you just say with the horizontal, it could have been below, above, and which side. If this says 10 meters at 25 degrees above the horizontal, all right, well, your horizontal line would be your x-axis. So it could have been 25, or it could have been 155. That's where it just says, read the problem for specifics. Okay, so now vector addition. And this is what we did back in 9th grade with the protractor and ruler. And we're going to learn that method again, but we're also going to learn the mathematical way to do it. So first, just think. Let's pick just a walking example. Okay, I walk 5 meters north, and then I walk 5 meters east. Okay, north and east. And I want to know, what was my total displacement, or what was my total, that's what I want to know, my displacement, final minus initial, but as vector. So if I walk 5 meters north, 5 meters east, what you can't just do is say 5 plus 5 is 10. Are you really 10 meters away from your starting point? No, because you made a little triangle there. So you've got to sketch it out. You need to draw a little sketch. And in that case, you could use Pythagorean theorem, but they're not always going to be nice 90 degrees. So anyway, so to do vector addition, sometimes they're simple enough to do in your head, sometimes you need to graph them out. I always suggest graphing them. Just start by drawing one vector. All right, and I kind of made this part up. Draw mini coordinates on the head of this vector, like a little mini x and y axis. I kind of made you do that in 9th grade. You don't necessarily need to do that, but visualize that being there. So you got a little x and y axis on the head of the first vector you drew. Then you use your little mini coordinates to draw the next one. And this will make sense with an example we'll do in a second. Do you guys remember what the answer was called? It started with an R. The answer is the resultant. And the resultant is a vector, so of course it would have a direction, which you would figure out by drawing from the tail of the first to the head of the last. That's how you would find your resultant vector, pretty much your answer. All right, so 4 steps. Here we go. And these, we're just going to sketch. We're not going to do these really to scale, but we're just going to sketch them. And kind of look ahead, kind of see where you're going. I mean, this one's east and this one's north. So I know I'm going to kind of really just need the first quadrant in my picture. Spacing can kind of help you out sometimes. All right, 10 meters due east. Okay, step 1, draw one vector. Okay, and I'll label it 10 meters. To the east. Starting at the origin. Step 2. That was to draw the mini coordinates. So here's the head of the vector I just drew. I'm going to draw another little x and y axis. Again, you can kind of just imagine that's there. But to get started, you might actually want to do that. And then I'm going to draw another vector. But like, ignore everything else you've drawn. Pretend everything else is gone. You're just looking at this little x and y axis. And you're going to start over again. So I'm going to draw another vector starting at my origin. 5 meters north. How does 5 compare to 10? Half, so don't make it the same length. Make it half as long. And it's still a vector, so it's still an arrow. Put the little arrowhead on there. So I drew one, I drew the mini coordinates, I drew the next one. And if I had more, I would just keep going. Just put another little mini coordinates. Keep going wherever you have to go. The answer, the resultant, tail of the first to head of the last. Where was the tail of the first vector I drew?
0, 0.
Yeah, right smack at the origin. The head of the last is right here. And I'll even label that R. So my resultant in this case is the hypotenuse. This makes a nice little triangle. Doesn't mean you'll always end up with triangles, although we often try to make triangles. But my resultant is a vector. It's got to have a magnitude and direction of its own. So how do you get magnitude? Pythagorean theorem. What did you say it one more time? Okay.
I know the resultant answer.
What is the answer for the resultant? Do it. 5 square root of 5? What's that? 10, 11?
11.18.
Okay. Okay. So you did Pythagorean theorem to get that. That makes sense. A squared plus b squared. That's kind of why I had you do that in the summer work as well. 11.18 meters, but that's not enough for my answer. It's got to have magnitude and direction, and I can't be skimpy and just say northeast. I need an exact answer. And since this is a triangle, and now you guys have had trig, you should be able to tell me that angle. How would you do it?
The tan.
Yeah. And I especially like
6.5.
tangent because these were your given numbers. Try to stick with tangent when you're finding the angle because 10 and 5 was given. Maybe you messed up getting the 11.18. Hopefully not. But so we know that tangent is opposite over adjacent. So our opposite was 5. Adjacent was 10. So you're doing inverse tan. All right, one more time, Erica.
26.5. And that was a
Oh, and it decided to tell you the answer anyway. Okay. Well, we had a little cheat sheet. So that is our answer. That's our resultant. That is what you get when you add those two vectors. When you add two vectors, your answer is a vector. So please don't forget the magnitude and direction part. Don't leave that off.
You don't need to add like northeast or anything.
You don't need to, no. You could have said 26.6 degrees north of east, but you don't really need to. Okay, so great. We added a vector. Let's do another one. Convenient. Okay, so here's just my coordinate system. You guys try this one. Tell me what you think the answer is. You got 12 meters per second west. We got a vote for 2 west. So, of course, no triangle at all in this case. Don't think they have to be triangles. So I went 12 meters per second west, and I've got 10 meters per second east. Maybe this is a boat speed and a river speed. And the east and west, these are the directions we're traveling. So what's like the net? What's the overall? What's the resultant? Tail of the first is back at our original origin. Head of the last is right here. So of course the answer is 2, but what direction should we put on our resultant? 2 meters per second. Yeah, is it 0, 180? And in this case, since you started with compass directions, this would be more appropriate to use compass directions. But yeah, is it east or west? West. Your resultant is pointing to the west. And of course, that should make sense anyway. You have a greater velocity west, greater speed west than you do east. So that was kind of one you could do in your head, but easy to see graphically. All right, let's look at that one real quick. 39. Checkpoint number 1 says the magnitudes of displacements A and B are 3 meters and 4 meters respectively, and C equals A plus B. But these are, they're bold, so they're indicating that these are vectors. Considering various orientations of A and B, what is the maximum possible magnitude for C? Yeah, 7.
Okay.
There's no way to get bigger than 7. And now how would you get a magnitude of 7? Just put them in the same line, put them in the same direction. So if that was 3 meters east and 4 meters east, then the resultant would have been 7 meters east. Okay, there's no other way to get a bigger magnitude than that. What is the minimum possible magnitude? Well, and when it says magnitude, the negative's irrelevant, just the number part. Good, just 1. And that would be, of course, if they're oriented how?
Opposites.
Yeah, opposites. One was east, one was west. The resultant magnitude would be 1. How could you get a magnitude of 5?
3, 4, 5 is, yeah.
Yeah. They'd have to be perpendicular to each other, like one east and one north. A 3, 4, 5 triangle, remember that?
Yeah.
Okay. All right. That was it for that. Back to the notes. Okay, so all well and good when it's at 90 degrees or in a line, but they won't always be. So how do we add them if they're not in a line? All right, first check and see if they are in a line. So this is, of course, if this doesn't work out, but it's an easy way to check, even if you're given, 0 and 90. You obviously know those are 90 degrees apart. But 45 and 135, just that much more thinking. But they are still at right angles to each other. So check to see if you have vectors that are right angles to each other or in a line simply by subtracting the angles they give you. If you find that when you subtract the angles you get 90 or 270, then those would make a right triangle. If 180 or 0, then they're in the same line, and it should be pretty easy to work with those. All right, but if they're not at right angles, first technique is graphically, and we will go through this really just once. Just make sure we have the basic idea down. So we're actually going to use a ruler and a protractor and sketch them to scale. So you write that, and I will pass out some rulers. Okay. So here are your steps real quick. Okay, so we got to come up with a scale, like 1 centimeter on my ruler equals, 10 kilometers, depends on what you're doing. Use your protractor for the angles. Draw your resultant, again, tail the first, head of the last. Determine the magnitude based on the scale, and use your protractor to find the ultimate direction. Okay, so if you work small, you could maybe fit this in this slide. Do you have space at the end? I don't know.
Yes.
You might want to do it there. You might want to do it at the very back of your notes just so you have a little bit more room. Let's see, where's my line? And again, I can already tell like where this picture is going to be. 15 degrees and 130 degrees. Okay, well 15's over here, headed towards the east. 130 would sort of be back the other way. So I really probably only need the first quadrant. So proper spacing will help. Bless you. And first thing you need is a scale. I don't even have units on my protractor or my ruler here, but I'll pretend those are centimeters. And 1 to 1 probably would work pretty well for you guys as well. So as far as the scale is concerned, we'll say 1 centimeter equals 1 meter. So I got a scale. I want to draw 10 meters, so I need to, draw out to the 10. But of course, I got to draw at 15 degrees. So how do you do that? How do you even know where 15 degrees is? Use your protractor. All right, let's remind ourselves how to do that. When you have your little protractor, you have a little pinhole here, like the intersection of 90 and 0. Put that on the origin. Okay. And if you drew, actually, if you drew the x and y axis actually at 90 degrees, then that should line up nicely. But so I just simply put my protractor here, and I'm just going to put a dot at 15 degrees. Now, please use your common sense. 15 degrees shows up twice on this protractor. Do I want the 15 degrees that's here, or do I want the 15 degrees that's here? In the first quadrant, you definitely want to put your mark over here. And just a dot. That's all you need. You just need to know which way to head when you make your line. Okay, so from there to there is 15 degrees. Common mistake, don't just connect the origin to that dot. You're headed that way, but that doesn't mean that's where your line should stop. Okay. So I've got this lined up with my dot to the best of my ability. It's obviously not a perfect technique. And I'm drawing, of course, all the way out to what?
10.
10. If I'm doing a 1-to-1 scale, I'm drawing out to 10. So go ahead and do that. You guys already finished. You ahead of me. Okay, don't forget your mini coordinates. This might be helpful in this scenario. Little mini coordinates where the y-axis is still up and down. It's not like tilted or anything. And the x is still left and right. Throw my protractor back on there, put the little pinhole over this new origin, which is really just the head of that vector. And I want to go to 130 degrees.
How do we know it's like perfect coming down?
To the best of your ability. Yeah, it's not a perfect technique. It's an approximation. So your protractor, like 90, should still be pointing straight up your page. All right, I'll find 130 degrees. Put a little dot. If it will let you. Okay. Get your ruler back out. Head towards the dot. This one is 5 meters long, so I only need to go out to 5 centimeters. Do that a little thicker. Yeah. Okay, so I've added the two vectors. Last step is to draw your resultant. Tail of the first to head of the last. So just your beginning point, your ending point. Connect them with your ruler. I'll make that a different color. And before I remove my ruler, I can tell what the magnitude should be already. Should be about what? Yeah, 9. Now, don't forget that you had a scale. Maybe your scale wasn't 1 to 1, but ours is, so that's pretty simple. 9 here is 9 meters in the world of the original problem. At, now I need an angle. Okay. Where do I put my protractor to get the angle of the answer? The original origin, back here. Because you, again, the answer is this green line, this green vector. You want to be able to tell somebody else how to draw that green line. So you already know you're going to tell them it's 9 meters long, but which way are they going to draw it? I need to know from my original origin which way to go. Okay, so put that pinhole right there. And just look. Of course, again, using your common sense. Is it between 130 and 140, or is it between 40 and 50?
40.
Between 40 and 50, I get like 43. Which, does it say on this one what it is? Doesn't say what that one really is. So it's not the exact answer. That's just really close to the right answer. Okay. The components method is the way to get the exact answer. But I'm actually going to wait on that until next class.